This is notes 2.3 compounds for pre-AP chemistry. And in your Pearson textbook, this is going to be pages 204 to 221, and also 278 through 313. And then in your study guide, it's going to be 83 through 94, and then 110 through 126. So this covers a lot of information. We're going to start talking about compounds, putting ions and elements together to form a compound, and also how to name those. So if you'll copy down this first chart, go ahead and pause the video, and then I'll come back and we'll talk about it. All right, so this chart just gives description of substances, like the different terminology, like elements, and compounds, and atoms and molecules. So if we look at atoms and elements, that's just going to be stuff in the periodic table, like neon, zinc, potassium. So those are just elements. Those are individual atoms. You cannot have a compound that is an atom. That's impossible. So you just can't have that. Elements that are molecules, this is like elements that combine with the same thing. And this is going to be O3, which that is called ozone. So when you hear about ozone, like in the atmosphere, O3 is ozone. And it's also going to be your diatomic elements. So hydrogen, nitrogen. There's also oxygen, fluorine, chlorine, bromine, and iodine, the diatomic elements. Now remember how we remembered those? Horses need oats for clear brown eyes. Those are the elements. And then, of course, you have compounds, that different elements that combine together to form a compound, or it's called a molecule. So we have H2O, you know, as water. That's a common one. CO2, it's carbon dioxide. That's also very common. And one that you've heard of, but you probably don't know the formula for, is ammonia. Ammonia is that really harsh smelling chemical, NH3. All right. All right, so go ahead and copy down these two charts, and then we'll talk about them. All right, so we have types of compounds. There's really 4 types of compounds that we're going to talk about: ionic compounds, molecular or covalent compounds, organic compounds, which are a division of covalent bonding compounds, and then acids, which are a subdivision of ionic compounds. So let's just talk about pure ionic compounds. How can you tell if something is a pure ionic compound? Well, it starts with a metal, and it forms a cation. For example, KCl is going to be an ionic compound. So we have KCl right here, ionic compound, and potassium is a metal. Now remember, on the periodic table, anything to the left of the stair-step line that starts with boron and then goes above aluminum, between aluminum and silicon on the right-hand side of the periodic table, anything that's to the left of that stair-step is going to be considered a metal, and anything to the right is a non-metal. So potassium is definitely to the left. It's in group 1. So that's going to be a metal. And then chlorine is going to be on the right-hand side, group 17, element number 17. That's going to be a nonmetal. So you have a metal and a nonmetal combining together. That's what an ionic compound is. And how do those atoms connect to each other? Well, since potassium has a positive 1 charge and chlorine has a negative 1 charge, the opposite charges attract and they stick together. It's called electrostatic attraction between those. So that's how those stick together when they form ions. Another one would be magnesium oxide. So you have magnesium, which is a group 2, so it has a +2 charge. And then you have oxygen on the right-hand side. It's group 16, so it's going to have a -2 charge. +2, -2 stick together, cancel each other out, so you have magnesium oxide. All right, molecular and covalent compounds. These are 2 nonmetals. An example would be carbon dioxide. So if you look on the periodic table, both carbon and oxygen are on the right-hand side of the stair-step line. So that's going to be a covalent compound. And the way that they bond is by sharing atoms between them. Carbon tetrachloride, CCl4, that is also a covalent molecule, covalent compound. They're both on the right-hand side of the periodic table. Now you see here hydrogen, and you may say, wait, hydrogen's on the left of that stair-step line. Well, hydrogen is an exception to this rule. Hydrogen is not a nonmetal. It acts like hydrogen is not a metal. It acts like a nonmetal. So it bonds in the same way a nonmetal would here. Organic compounds. Organic compounds usually start with the CH. So examples here would be C2H6 or C6H12O6, C3H6O. These are all organic compounds. And again, those electrons are shared between the atoms. And then this last category, acids. Acids start with an H, except for H2O and H2O2. So except for water and hydrogen peroxide, anything that begins with an H is going to be considered an acid. And I have a little correction to make here. This 2 should be a subscript 2 and not a regular big 2. All right, so here we have examples. HCl, that's hydrochloric acid. H2SO4 is sulfuric acid, and then HNO3. And even though it says here that electrons are shared between atoms, it is, but it's also, it's kind of weird. Acids they share electrons, but they bond in the same way as ionic compounds. So your hydrogen here has a +1 charge, and chlorine has a -1 charge. So those cancel out, okay? SO4 is a -2 charge. So you have to have 2 hydrogens, 2 +1 charges to cancel that -2 out. So it's kind of like ionic and covalent at the same time. All right, so here we have some more examples in this chart here. So if you're looking at just this compound, calcium chloride, how do you know if it's ionic, covalent, organic, or an acid? Well, you have to look at what's bonded. So we have calcium and chlorine, and this is going to be ionic because calcium is a metal, chlorine is a nonmetal. And then we have C3H6O. Okay, so you see the CH there. That means it's going to be organic. And then HF is our next example. Okay, this begins with an H, and it's not water or hydrogen peroxide, so that's going to make it an acid because it begins with H. And then going over to the second column, P4O10. So if you look at phosphorus, that's a nonmetal. Oxygen is a nonmetal, so those are 2 nonmetals, so that would make that covalent. H2SO4, all right, so it begins with an H, but it's not water or hydrogen peroxide, so that's going to make it an acid. And then the last one, barium nitrate. Okay, barium is a metal, so we don't have to go any further because we know barium is a metal. This is going to be ionic. And this is metal can be bonded with anything. So here it's bonded with what we call a polyatomic ion, NO3. We're going to talk about those in just a moment. But if you recognize this first element as a metal, you can automatically say it's ionic because it really doesn't matter what it's bonded to in the anion, the negative ion there. All right, so go ahead and pause this video and write this down. These are the characteristics of ionic compounds, which are also called salts. All right, ionic compounds are typically hard solids with high melting points. So if we think about table salt, sodium chloride, it has a very, very, very high melting point. And there are even YouTube videos where they show people melting salt. Okay, they have to heat it up in a special heating container get it really, really hot. You can't melt salt in your oven like you can sugar. Ionic compounds do not exist as molecules, so individual units are called formula units. Ionic compounds dissolve in water. It's said to be soluble, and it breaks up into ions. So our picture here that we have down in this corner here, it shows like this is the crystalline structure of sodium chloride. Then when you put it down into water, these red and white molecules here are the water. So the water, the positive side of the water starts surrounding the negative chlorine ion and pulls it apart from the sodium. And then the negative side of the waters start surrounding the positive sodium ions. And so that they pull them apart and they just surround. That's how sodium chloride dissolves. In an ionic compound, the positive and negative charges cancel out to form a neutral compound, and that happens every single time. And we're going to look at this characteristic here, and we're going to be forming ionic compounds. If you use more than one ion, you need to use subscripts. If you use more than one polyatomic ion, you use parentheses, and we're going to go over these rows and do some examples of those. And to name an ionic compound, you first write the name of the cation. So that's the positive ion here. So in this example of sodium chloride, sodium would be the cation. So you just write the name of the element. So it's just going to be sodium. Na is sodium. And then the anion, if the cation is a metal that forms multiple ions, you use Roman numerals. We're going to talk about that to indicate the charge. So when we write the anion, the negative part, we take off the ending. Okay, so this is going to be, for this example, sodium. So I'm going to go ahead and write the name of that one without any changes. And then chlorine is the second element. We're going to take off the ene of chlorine. We're going to change it to ide. So the name of that molecule, that compound, is sodium chloride. And we'll talk about Roman numerals in just a moment. All right, so let's write down the definition of polyatomic ions. So go ahead and pause. All right, a polyatomic ion is a group of elements that's bonded together that have an overall charge and that bonds to other ions like it would be a single element ion. Okay, so NO3 is a polyatomic ion. It's two elements, nitrogen and oxygen, that have bonded together, and the overall charge is a -1. And it acts just like chlorine. In our previous example of sodium chloride, since it has a -1 charge, it will act exactly like chlorine. So we could bond sodium, which has a +1 charge, with nitrate, NO3, that has a -1 charge. And so this would be sodium nitrate. All right, these ions have specific names. We don't change those. The ion is called nitrate, and that's this right here. Okay, most but not all, unfortunately, polyatomic ions end in either ate or ite. The rest you're just going to have to memorize. All right, so let's look at some polyatomic ions. All right, so first let me talk about the periodic table. So you'll see on the periodic table these numbers, the periodic table that I gave you. This isn't on all periodic tables, but it is on the one that I gave you glued in. All right, so you see above these groups, it has charges. Okay, those are the charges of the ion that group forms. So all of these group 1 elements will form a +1 ion. And all of the second group, +2, etc., across the periodic table. And that's for single elements. Now we have polyatomic ions. And I'm going to be giving you this list in class of these polyatomic ions. So you'll have them to look at. And we are going to take some quizzes on these. You have to memorize these. I'm sorry, there's 3 separate quizzes. One, this is the first quiz, this first column. The second column is the second quiz, and the third column is the third quiz. So we'll have 3 quizzes on you memorizing these, and you have to memorize the formula, the name, and this charge. All right, so all of these are polyatomic ions. They're 2 or more elements that have bonded together that act like a single elemental ion, like from the periodic table. And we don't change the name of those. So say, for example, the nitrate that we were just looking at is right here, nitrate. It's an NO3, all right, that never changes its name. So when it's bonded with something, these never change their name. You just use the name as is. All right, so let's go back to here. Let's look at how ions combine together. So here we have a calcium ion and a phosphorus ion, and these are what is called Lewis dot structures. So if we look at calcium on the periodic table, oops, wrong way. Wait, hold on. It's right here. If we look at calcium on the periodic table, let me get this out of the way. Right here is calcium. Okay, calcium is in group 2. That means it has 2 valence electrons. And so when we write the Lewis dot structure for calcium, we put 2 dots. And so those are the 2 dots that represent that. I think I talked about this earlier. Phosphorus, we see here phosphorus has 5 dots. So if we go over here to the periodic table and find phosphorus, which is right here, we see it's in group 15 or 5 valence electrons. Okay, so that's how we draw the Lewis dot structures. So in order for these to bond, calcium wants to lose its electrons because it's a metal. All metals lose their electrons, so that the orbital or the shell underneath those 2 can have a full valence shell, and it can be stable. And then phosphorus, since it's on the right-hand side, it's a non-metal, it wants to gain electrons. So right now it has 5 valence electrons, and it wants to gain up to 8. So remember that magic number 8. So what happens, and you have to do these drawings a lot, is this electron will come over and sit here, okay? This electron will come over and sit here, so it'll have 2 on each one of those sides. And so we've run out of electrons for calcium. So what we're going to have to do is add another calcium. You have to keep adding until they equal out. So this electron is going to come over and sit here. All right, so now calcium has 1 electron left over. So we have to balance that out. So now we're going to have to add another phosphorus. And so this can come over here. So now we've used all of our calcium electrons, but phosphorus still doesn't have 8. So now we're going to have to add another calcium so that this electron can come here. And then finally, this electron can come here. So all of our calciums that we have here have lost all of their electrons. And then the phosphorus that we had to add, both of those phosphorus now have 8 electrons. So now this compound is balanced out. So when we write the compound, that's going to be Ca. And how many do we have to use? 3. So we're going to have to put a 3 there as a subscript. And that bonded with phosphorus. And how many phosphorus did we use? 2. So the correct ionic formula for calcium phosphide is Ca3. I'm sorry, Ca3P2. So again, let's review naming this. So this first element, we don't change its name, so we write calcium. And then this is phosphorus. Okay, we're going to change the ending to ide. So we're going to drop the ending and add ide. So this is calcium phosphide. Okay, now there's another way to do this. And let me move these out of the way. You can either do it this way, or you can do what we call, move the calcium up here, swap and drop. And this is an example here of swap and drop. All right, so what we're going to do is we're going to take the charge of calcium and phosphorus. So the charge of calcium is going to be +2. So we're going to put a +2 there. And the charge of phosphorus is a -3. So it's 3 negative. Well, to get the correct formula for this, we're going to do what's called a swap and drop. So this 2 is going to swap over to the phosphorus, but if you follow the dotted line, we drop it down into a subscript. And then this 3, we don't take the charge. Okay, so the charge doesn't come with it. So it's not going to be phosphorus 2+, just the number. And then we take the phosphorus, which is a charge of 3 negative or -3. We're going to leave not worry about the charge. We're going to take this 3, follow the solid line. We're going to take it over to calcium and drop it as a subscript. And this works every single time for ionic bonds. Now this is only for ionic. So that tells you the formula, Ca3, P2, which is exactly the same way we did it when we moved electrons. So whatever way's easiest for you. For me, I prefer the swap and drop method, but whatever is easiest for you, that's the method that I want you to use. Okay, so let's look at some examples. We have calcium, which is a +2, and we have oxygen, which is a -2. That's the cation ion. Cation ions are always positive because cats have pause. Anions are always negative. And if you look at the word anion, A-N, it's always negative ion. All right, so that's just a little trick to help you remember. Cations and anions. All right, so we have +2, -2. So those charges cancel, so we don't have to do anything except smash them together. So the correct formula would be CaO. So if the charges cancel, you don't have to swap and drop, anything like that. All right, so what's the name of this? Always calcium. And then oxygen, we change the ending to "ide", so it's oxide. So this is calcium oxide. All right, so the next example, calcium and chlorine. Calcium is a +2, chlorine's a -1, so those are different. So we're gonna have to swap and drop. So calcium gets the 1, but we're not gonna write 1s. And then chlorine gets the 2 as a subscript, so CaCl2. Okay, and the name of this is calcium chloride. Calcium chloride. All right, so go ahead and pause the video here and do the other 2, and then come back and we'll have the answers for you. All right, so swap and drop. The calcium is +2, -1. So we're gonna have Ca, it gets the 1. But then the nitrate here, NO3, we need 2 of those. So I bet some of you did this. Okay, so what does that look like? It looks like we have NO32. All right, so that's going to be wrong. If you have more than one polyatomic ion, we need to some way separate that 3 and 2. And the way we do it is by putting parentheses around it. So this is going to be parentheses NO3 and then the 2 on the outside. And this is a polyatomic ion, so this is going to be called calcium. And then we keep the polyatomic ion. If you look up NO3, that's a nitrate. So it's calcium nitrate. All right, on this next one, we have Ca, and then we're going to have a subscript 3 for swap and drop. And then PO4, we're going to have to put in parentheses because we need 2 of those. We don't want it to look like 42. So the name of this is calcium, and then PO4 is a phosphate ion. So it's calcium phosphate. All right, so on your next column here, we have Na2O. All right, so the name of that is sodium oxide. Okay, for the oxygen. So what's the cation and the anion? Well, this is where you're going to have to swap and drop, or unswap, undrop. So you have to know that this 2, unswap it, you're going to bring it over here, and that's going to be negative, because when you form compounds, the positive one always comes before the negative one. So the second element's always going to have the negative charge. So this is oxygen -2, or you could just look on the periodic table that I gave you. All right, and then the sodium, okay, there's no number here for a subscript of oxygen, so that must mean the sodium is a +1. So we just write a plus there. All right, so aluminum, I'm just going to write aluminum. Okay, and then C2H3O2, that's the acetate ion. So this is aluminum acetate. All right, aluminum, it's going to be +3 because the acetate has a 3 subscript. The aluminum doesn't have a subscript, so that must mean that the acetate is a -1 charge. And I don't have room to write the whole acetate, but it's going to be C2H3O2. There, I did it. All right, copper chloride. Copper is a transition metal. So the only way that you can get the charge of copper is to unswap, undrop. So look here, this has a 2, so that must mean that copper has a +2 charge, okay? +2 charge. Well, since this is a transition metal, we have to write the name just a little bit different. All transition metals except for zinc and silver are going to get Roman numerals. So you just have to memorize that zinc and silver do not get Roman numerals. And if we look at our periodic table, zinc and silver are right here together diagonally. Okay. So zinc is always a +2 and silver is always a +1. So it's in line with aluminum. So the way I remember that is 3, 2, 1. Aluminum is always a +3. So zinc is going to be a +2 and silver will be a +1. So it's 3, 2, 1. That's just how I remember it. All right, so since copper has a charge of 2, this is where you have to use a Roman numeral to indicate the charge of copper. So this is going to be copper 2, and this is going to be chloride. Okay, copper 2 chloride. All right, so the last one, we have to recognize that CO3 is a polyatomic ion. That's why I make you memorize these polyatomic ions, because if I just tell you how to remember them, you don't. So if I make you memorize them, then you remember them. So here is CO3 right here. Carbonate has a -2 ion. So that means that iron must be a +2 because there's no subscripts there, and this has to balance out to neutral. So if the carbonate's a -2, the iron has to be a +2. So this is going to be iron. And since it's a transition metal, 2, iron 2, and then carbonate, because that's the carbonate ion. Okay, so that's a little bit different. If you need to watch this over again, then do that, just this section. All right, so forming ionic compounds with transition metals, that's what we just did. Okay, if you need practice on this, we'll do this chart in class and practice some more on this one. All right, so let's talk about naming covalent compounds. So pause and write this down, please. All right, so covalent compounds can be solids, liquids, or gases in standard states and usually have much lower melting points. The electrons in a covalent compound may be unevenly distributed, which results in a polar compound. And we saw polar compounds when we did the chromatography lab. Polar compounds dissolve better in water than nonpolar compounds. However, they do not form ions. So they stay stuck together. They just dissolve amongst themselves, separate themselves like sugar. To name covalent compounds, state the non-metal elements, and then the last element should be changed to have an "-ide" suffix or an "-ide" ending. We only use prefixes. We use prefixes for every single element except The only exception is if there's only one of the first element. So let's look at some examples. All right, so here we have, and here are the prefixes. Forgot to tell you that those are the prefixes that we're going to use. All right, so here we have Xe, which is xenon, and we only have one of xenon. So that's this exception to the rule. We're not going to use a prefix in front of that. So this is just going to be xenon. Then we have fluorine. We have 4 fluorines. So let me erase this so we can see this better. So the prefix for 4 is tetra, right here. So this is going to be tetra fluoride. Change the ending to ide. So the name of that is xenon tetrafluoride. That's a Fluoride. All right, so the next example, we have phosphorus, but we have 4 phosphorus, so that's going to be tetra phosphorus. We don't change the ending to phosphorus on the first one. We only change the ending on the second one. And we have 10 oxygen, so the prefix for 10 is deca. So this is going to be dec. We have dec, we have an A, and then this is oxygen. So we don't put 2 vowels together usually. So we'll drop the A off and call it decoxide. The ending changes to ide. So this is tetraphosphorus decoxide, the name of this one. All right, and so going the other way, dinitrogen, that means that we have 2 nitrogen. Monoxide, so mono is 1, oxide is O, so the formula for that is N2O. Oxygen, okay, so that doesn't have a prefix, so that tells us there's just one. Dichloride, chloride comes from chlorine. Di means there's 2. And that ends our video for today. I'm going to come back and do another video just naming acids because there's a lot of rules for that, and this video has become long enough. So make sure you like and subscribe, and please hit that bell button so that you know when I put up other videos.